Alright, welcome to the last video, woohoo, of the semester. Woohoo! That's even better. Now, in this video, we're going to kind of continue with something that we talked all the way back at the beginning of the semester with radicals. And also, we're going to finally talking about imaginary numbers. And let's just go ahead and get to it. Alright, so you are given something like this, square root of 12, and your job is to simplify it. Go back to what I've told you before. You can put this in the calculator and you're going to get some funky looking number. We don't want to do that. When I say simplify, I want you to pull out anything that's a perfect square. So what can we factor 12 to become? Well, you should remember that we could factor out to be something like this. This should ring a bell. We know that 4 times 3 is 12, and so it's really saying the square root of 4 times the square root of 3 is the square root of 12. Well, what's the square root of 4? 2. So what's my final simplified answer? The square root of 12 is really 2 times the square root of 3. Okay, easy peasy. Alright. Well, this is something we didn't do. Square root of x to the 8th power. Alright, so in the last video, I kind of showed you a little something that could actually help you solve this problem. There's several ways that we can do it. Really what it's asking for is how many groups of 2, how many x's in groups of 2 can you pull out of this thing? So let's show you the hard way, and then I'm going to show you an easy way. This thing is saying x times x times x times x times x times x, right? Well, since this is a square root, it's asking me how many different groups of 2 are there. Well, that's a group of 2, that's a group of 2, that's a group of 2, that's a group of 2. So ultimately it's x to the 4th power. Alright, makes sense because there are 4 group of those x's. That's how this kind of works, but I like doing it a different way. And this kind of helps me, and it may help you. A while ago, I told you that when we are square rooting something, we're actually raising it a number to a fraction. So in this particular case, I'm actually saying x to the 8 divided by, or 8, excuse me, x raised to the 8 halves. Okay? That's really what this is saying. Remember from the last video that we talked about this. Well, what's 8 halves? X to the 4th. To me, this is a quicker understanding of the concept, is when I'm raising, taking a power and I'm finding what the radical is. In this case, I'm finding the square root. I'm really going to say 8 divided by that 2 that's here. Alright, so let's try another one. So in this one, I'm looking for how many groups of 3 I can actually pull out. So again, we can do it this way. I can say 1, 2, 3, 4, 5, 6, 7, 8. So I've got 2 groups of 3. So that's going to be x squared. But then I got these 2 that I didn't circle. Well, they're what's left. Alright? Because I can't pull out x squared when I'm cubing it, asking for the cube root of it. Alright, so let's do this another way. This is really saying x raised to the 8/3 power. So you need to ask yourself, how many 3's can I pull out of 2? This is basic division. Well, you can pull out 2 of them, alright? With a remainder of what left? 2, right? Think about division. 8 divided by 3 is 2 with a remainder of 2. So that first 2, which is 2, you write it down. X to the 2nd power. Then it says with a remainder of 2. Well, that's really saying this. Alright? Or we can factor out x squared, and what's left is this guy. So we can actually prove this a couple of different ways. If we raise this to the 3rd power, we're going to get 8/6. Multiply it by the x square, what do we get? We get our x8th again. And it's all this one vicious cycle. Personally, if it helps you to draw all the x's like I just did, it's legal. But if you can understand that it's really asking you how many groups of 3 can I pull out of this 8 and what's left over, then that's the way you need to do it. You know you can pull out two full groups of 3, that gives me my x squared, and my remainder is the 2/3. Or I can say x squared times the cube root of x squared. Alright, let's go to 4. These I just kind of want to do with you. So we have 12 x to the 7th, y to the 3rd, all being square rooted. Alright, so let's look at it individually. The square root of, what can we pull out of here? We know that this, if I just break it down individually, alright, so all of this is equal to that. I've just broke it down. We've kind of done this before with other factoring. We know we can break this down even farther, and we can say that this is 2 times the square root of 3. How did I get that? I factored out a 4, remember? Well, what's happening here? I'm asking how many groups of 2 can I pull out of this x to the 7th? Well, I can pull out 3 groups of 2 because I know 3 times 2 equals 6, and what's left over is the 1. So since I'm pulling out 3 groups of 2, it's x cubed times the square root of x. Same principle here. How many groups of 2, because this is a square root, am I pulling out of this y to the 3rd? Well, I can only pull out 1 group of 2. So that's just going to be y raised to, well, what's my remainder after I pull out that 1 group of 2? It's just going to be 1 again. So now I've broke it up, each individual piece, okay? But now let's smash it all back together again. Everything that's outside of the radicals can get multiplied. 2 times x to the 3rd times y gives you 2x to the 3rd y. Now we're going to smash all the radicals together. And I'm going to say square root of 3xy. Okay? Now, let's do 6. I'm going to skip 5, let you work on that on your own. We'll go right straight to 6. 6/8, and this one's tough because look at what it's actually asking. It's not asking for anything you're used to. It's asking for the 5th root of 6,561 times x to the 9th. Let me rewrite that. X to the 9th and y to the 11th. Alright, so what we want to do is we want to factor each individual piece first. Now we can do it all in one swoop, but I like factoring each individual piece. So it's asking for the 5th root of 6,561. We're going to multiply that by the 5th root of x to the 9th, and we're going to multiply that by the 5th root of y to the 11th. Alright, so let's get this guy done first. So we need to kind of look at our numbers of what we might be able to factor out that is a 5th power of a number. That's the way I will say it. Alright, so let's just kind of look at some numbers. Well, 1 to the 5th power, if I try to factor that, well, 1 to the 5th power is 1. That's not going to work. So let's try 2 to the 5th. And what we do is when we get 2 to the 5th, that's 32. I'm not even going to attempt to try this one because it seems mighty low. That's a big number that I've got behind me, 6,561, and only try to factor out 32. That seems a little silly. So let's try 3 to the 5th and see what it gives me. Well, this one gives me 243. So can I factor that out of 6,561? So let's find out. 6,561 divided by 243. Just like so. What's that give me? It gives me 27. Hey, this might work because I know that I can't factor out anything out of 27 that's a fifth root. It won't work. Okay? So, what did I just discover? I just discovered that I can say 3, because 3 to the 5th power was at 243, times the square root of 27. Excuse me, 5th root of 27. So this number and this number are the same thing. I just factored out 243, which happens to be 3 when I find the 5th root of it. Alright, so this number is majorly big, but it still follows the same procedure like if I was finding the square root of 12. Nothing changes, except this time instead of square root, I'm finding the 5th root. Alright, so we've got that. And I'm going to move this 3 over just a little bit so you're not getting confused. So this is 3 times the 5th root of 27. Well, here we go now. This is asking how many groups of 5 can go into this 9. Well, we can get one group of 5 with a remainder of 4 left over. Okay? This is asking how many groups of 5 can I get out of this y to the 11th. Well, this time I can get 2 groups of y with a remainder of 1 left over. So now we can kind of plug everything together. My outside terms can get mushed, and that gives me 3 times x times y squared. My inside terms can get split together. I get 27 times x to the 4th times y. So this, factored out completely, or excuse me, or we try to simplify the radical, that's a better statement, is 3xy squared times the 5th root of 27x to the 4th times y. I'm going to leave number 5 for you. If you got questions, bring it to me on class. Alright, so let's keep on trucking. I'm not even going to pause the video. Now, this next one, it says rationalize the denominator. We've already done this in this class. It snuck up on us last module, I think, and it just snuck up on us by accident, and it was supposed to show up later in the semester, but they goofed up, or I goofed up, who knows, somebody goofed up. I blame you. Yeah, you know who I'm talking to. So, I am going to say that I need to rationalize this number. Well, what does this mean when I say rationalize the number? Another way I can write this happens to be the square root of 13 divided by the square root of 5. Just like, well, let me rephrase this. Basically, it means this. To rationalize the denominator means that if I have a radical sign in it, I need to get rid of it. And because I don't like it there. And in order to get rid of a radical sign, I need to multiply it by itself, such as this, right? But here's the problem. Think back. If I want to change a number without truly changing the number, I can only do a couple things. One, I can add or subtract 0, or I can multiply or divide by 1. Remember that? Same concept is happening here. In order for me to get rid of this without physically changing the number, I need to multiply it by the number 1, because the square root of 5 divided by the square root of 5 is 1. So it's not going to change anything, it's just going to make it look different. Alright? So I'm rationalizing the denominator by basically multiplying it by itself as a 1. Alright, so what happens here? Well, 13 times 5, that gives me the square root of 65. Because the square root of 13 times the square root of 5 is the square root of 65. Divide by, well, what's the square root of 5 times the square root of 5? Square root of 25. Now, some of you probably figured out something really quick. If I multiply a square root by a square root, guess what I get? Just the number that's under the radical. So I can really say that this is the square root of 65 divided by 5. But wait, there's more. So the next question that we need to ask ourselves is, can this be simplified any farther? I don't know. So it says 65, so I'm going to divide 5 out of it. What's that leave me? Well, when I do 65 divided by 5, it leaves me a 13. So really, there is no perfect square I can factor out of this 65. So I have simplified this all the way. Now, let's say for the sake of argument, and we might run into something here soon, that you came up with this answer. Okay, let's say we came up with this as an answer after we've done after we've rationalized the denominator. We know what we have to do here is we need to simplify this any farther. So what can I factor out of 24? Well, I can factor out a 4. And that leaves me with 2 times the square root of 6 divided by 2. Okay? Well, what happens here? Well, these 2 are going to cancel out. So this ultimately becomes the square root of 6. So be aware of that. Sometimes when you rationalize the denominator, your numerator can be simplified even farther, and your denominator and your numerator may end up canceling out, just like it happened in here. So be cautious of that. Alright, so let's go ahead and try, I'll leave number 2 to you. Let's try, let's go ahead and try 3, and we'll do 4 next. Alright. Okay, so we can rewrite this to say it's the square root of 9y to the 9th over the square root of x to the 4th. Okay? Now, we can do this a couple of different ways. Your instinct might be, well, let's just think about it. Can we simplify this top part before we do anything else? Yes, we can. What's the square root of 9? Happens to be 3. How many times can I pull out a 2 out of y to the 9th? I can pull it out 4 times. With what left over? A y left over. Divide by, well, what's this? It's going to give me x to the, 2nd. So really, that was all that was done for that one. Alright? So, this one, I rationalized it, but what I did before I even started to do anything, I just kind of, alright? So there's nothing too straightforward on that one. Nothing too bad on that one. Alright, so what I'm going to do is, I was going to show you 3, I decided against it. I'm just going to let you work on that one and try it on your own. If you got questions, you know how to find me. This one I do want to take up with. I have square root of c minus 5 divided by c plus 5. Now, I need to rationalize the denominator. So, another way I could write this to kind of simplify my life is the square root of c minus 5 divided by the square of c plus 5. Okay, it's the same thing as what I originally did. Now, what I need to do is rationalize this denominator by multiplying it by itself. But the thing is, in order for me to really do this, I also have to have a numerator that happens to be the same thing. Why has this got to happen? Because I can only multiply a number by 1 in order to change its looks, but not change its value. Alright, so that's what we're doing here. Alright, so let's do it. What happens here? Well, they multiply, blah, blah, blah. Guess what you get? C plus 5. Basically, like I said before, when I multiply a square root times itself, it just kind of cancels out the square root. This gives me 6 plus 5. What we've got happening now is that we're taking this square root of c minus 5 and multiplying it by the square root of c plus 5. I can rewrite this to say the square root of c minus 5 times c plus 5. All of this is being square rooted. Now, so that's c minus 5, c plus 5. Multiplying those two together. Wait a minute. Ding, ding, ding. Alarm bells, or boom, boom, drums, whatever, trumpets. what should be going off in your brain? What is happening here? What does this look like? Difference of squares. So, when I have a difference of squares, c minus 5, c plus 5 being multiplied, look what I'm going to write down. I'm going to say c squared minus 25. Alright, so it's the square root of c squared minus 25 over c plus 5. Now, you may be wanting to do this and square root the c squared and square root the 25. Don't. Think back to first module. You remember how I gave you something like, I don't know, we're going to use numbers like this again. C4 plus, how we had square root of square root of 4 plus 8. I cannot square root this right now. I have to add it first, right? And then I could finish it out. Same principle. I can't do anything else to this until I combine them. But this is apples. This is oranges, so they cannot combine. So this is as far as I can take it. So basically, long story short, we're going to multiply to rationalize, we multiply it by whatever the denominator was and make sure that we're doing it as a 1 and not just whatever. It has to be equal out to 1. Solve for it, and you're done. Alright, so that's basically rationalize the denominator. You're basically just multiplying it by the denominator and having the numerator in there as well. Alright. Cool. So now the thing that confuses everybody the most, imaginary numbers. Woo! Alright, imaginary numbers. Well, for lack of a better term, in a mathematical standpoint, are not real. Okay? There are all sorts of types of numbers there are whole numbers that you're used to, there are integers, there are negative numbers, there are rational numbers, and all sorts of stuff, and it's what we call a number theory. And then there's this group of numbers that we don't even know if they exist, but we use them and call them imaginary numbers because they help our equations work. I don't know, it happens to be that way. And basically, we define an imaginary number as this. J is equal to the square root of -1. Alright, so go back in your mind to the very first series of lessons we did, and I told you that you should never, ever, 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 ever get the square root of a negative number. When you do, it's going to become an imaginary number. Okay, so here's the thing. Why are we, J, that's just silly. Why are we saying that J is an imaginary number? Why can't we say that I is an imaginary number? That's a good question. Guess what? In mathematics, this is what we use. We use I for imaginary number. However, because we're in more of the technical line of mathematics that we're kind of doing, I actually pops up into some electrical equations and things like that, so we don't see I in industrial settings, so we use J instead. But in algebra, higher end calculus and stuff like that, we tend to use the letter I. But for this class, we're going to define the imaginary number J is equal to the square root of -1. So, what does this mean? Alright, so, here we go. I have -36, and I'm trying to find the square root of it. You need to break this down into its individual factors. One, we know that this is going to be -1 times 36. So far, so good? Because we broke it up. We need to pull that negative out. Well, what do I now know? I know that this is -1 times the square root of -36. This works just like simplifying a radical. I can't think of the term I want to use, but it's the same concept. We're just factoring things. Well, what's the square root of -1? It's an imaginary number, and we put J. Well, what's the square root of 36. 6. Well, these two things are being multiplied, so we write it as 6j. Alright, now, you won't normally see j in the equation. You haven't seen j this semester in the equation, other than maybe me just giving up whatever, because we define j as an imaginary number. So the square root of negative 36, we factor out the negative 1, it's imaginary because why? It doesn't exist. Just like I told you, there is no known number in the universe that multiplied by itself will equal negative 1. Just like we said all the way back at the beginning of the semester. So it's an imaginary. Square root of 36 happens to be 6. Multiply together, 6j. Alright. Next one. Alright. So we have a negative on the outside, so we don't want to forget that. We're just going to write it down. Factor this thing. We know that this is going to be negative 1, okay, because there's a negative there. And we know that this is going to be multiplied by the square root of 144. Well, this would be negative, stays there. This becomes a j, that state goes there. This becomes 12. Multiply all this together, I'm really saying negative 12j. That's our answer for this one. Now, after a while, in all truth and honesty, if you see a negative, you know you're going to have a j. So really, you don't necessarily have to do this step each time. It is a good thing for you to kind of remember that, hey, I'm factoring out that square root of a negative 1, which is my imaginary number. And then you can work with this side, which is your actual regular number, okay, just like you normally would. In this case, we had that negative, so it never went away. Why did it not go away? Because it was on the outside of the radical. So it's just there. Alright? Yeah, let's keep going. We're doing good. We're doing good. 4, I think I'm going to stop at this one because I'm going to let you do the next one on your own. Alright, so 4 times the square root of negative 8. Alright, so we have a 4 on the outside. I'm going to keep them there. We know that there's a negative 1 here, so I'm just going to go ahead and factor it out because we know the square root of negative 1 to be j. So I'm just going to write that there just to get it out of my way. What's left is the square root of 8, right? Well, what can we do here? Well, we know that the highest perfect square we can factor out of that is 4, so we can rewrite this to say 2 times the square root of 2. Well, what happens with all of this? They multiply, and I get 8j times the square root of 2. Don't like that way? Let's do it one more way. I could say 4 times the square root of negative 1 times the square root of 4 times the square root of 2. Why that? Because negative 1 times 4 times 2 is negative 8. Well, this is going to give me 4 times j times 2 times the square root of 2. Multiply all this out. 8j times the square root of 2. So different ways to do it. As long as you can see it, I'm happy. Alright. Complex numbers, essentially this. I take an imaginary number and I'm adding it to a real number. Okay? That's really all it is. So far, all I've done is just imaginary numbers. Even though this is 4j, this is an imaginary number for the simple fact that it's j times 4. It's imaginary. It doesn't exist. However, if I put this in there, it's no longer an imaginary number but a complex number because it has an imaginary part and a real part because 3 is real, 4j is not. Basically what that tells us is that we can define a complex number as a plus b times j, where a is a real number and the bj represents the imaginary portion. Okay, so we have different ways of doing it. So basically I could say that a complex number happens to be 4 plus 5j. Alright, 5, and that's a complex number. Now, working with complex numbers is very simple. You kind of treat the j like really you treat the j like an exponent, except for one little caveat later on, and we'll explain to it. When we go to multiplying, you treat it a little different. But when adding and subtracting, you kind of treat it like it's an exponent. Not an exponent, but a the words variable. There you go. That's the word I'm looking for. You kind of treat it like a variable, except for when you start to multiply. Let me show you what I mean. All right. So I have the first one, 3 plus 5j plus 9 minus j. Okay. Like I said, we treat this like a variable, okay, at first, okay? Combine your like terms, guys. That's all I'm really meaning. 3 plus 9 gives you what? 12. So I've combined that term and that term. 5j plus a negative j gives me 4j. I'm done. Okay, see how I just treated it like a normal variable? I just combined my like terms. So this is only good when I'm adding and subtracting. Alright, so your next one, just you can figure out 2 on your own. Let's just go on to 3. That looks more fun. You have negative 3 plus 4j minus a negative 4 minus 4j minus 2j. So we're going to combine like terms. Negative 3 minus a negative 4 is basically saying 3 plus 4, so that gives me 1. And that's it. So that's going to give me 1. Make sure. Negative 3 minus a negative 4 gives me a positive 1. Very good. So we've got that part. Now we're going to combine our j's. 4j minus a negative 4j, well, that's going to give me 8, because minus a negative is positive, so 4 plus 4 is 8. Minus 2 again gives me plus 6j. Alright, so nothing hard on that one. Now, what really gets interesting, and we're almost to the end, is when we start to multiply j's. We're not going to go but so far with it. All we're going to do, I'm saying j's, but I mean imaginary numbers, you know what I mean. If I take a j and I multiply it by another j, imaginary number times an imaginary number, this is really saying negative 1, the square root of negative 1, times the square root of negative 1. Go back, I've told you this before. If I take a square number and multiply it by itself, what I have is what's actually under the radical sign, or the radicand. So really, the square root of negative 1 times the square root of negative 1 is equal to just negative 1. So what we say is this. We say that j squared is equal to negative 1. This is a key rule with working with imaginary numbers. Now, we also do, when you get into higher end algebra and stuff like that, we find out what j cubed is, j to the 4th, j blah blah, j blah 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 blah, all the way up. And it's pretty simple, but I'm not going to go into that in this class. We just need to know that j squared is simply equal to negative 1 every time. So that's where this difference. When we're adding and subtracting complex numbers, we treat the imaginary number, we treat j like a regular variable. But when we start multiplying them, we have to remember that j squared is always equal to negative 1. It's a key thing to remember. Alright, so let's go with it. We have 3j times 4j. Okay? So we're going to treat this at first like a normal variable. 3 times 4 is 12. And j times j is j squared. But remember, j squared is really saying negative 1. Alright? So really, ultimately, my final answer is negative 12. 3j times 4j gives me 12j squared, or 12 times negative 1, or just negative 12. Alright? Next. All right, we're going to multiply using distributive property. 3j times 4 gives me 12j. 3j times negative 7j gives me negative 21j squared. All right, so this is 12j minus 21 times j squared is going to be negative 1. I love saying that, by the way. 21. If you know what I'm talking about, you can laugh. All right, so 12j minus 21 times negative 1. Well, minus 21 times negative 21 happens to give me 12j plus 24. Now your instinct is probably saying, hey, I'm done, and technically this is correct. However, your homework asks you to write it in this form. Is asking you to write it in a plus bj form, where a is the real number. So my real number is 24 plus my imaginary part, which is 12j. And generally, this is what is accepted in the real world. This is correct, but it's not in the correct way of saying it. I know that seems very silly, but it's very beneficial later on in higher end mathematics, and having this organized so you don't lose your mind. Okay, that's what this is about. So after you get your answer, make sure that you have it in this form, a plus bj. All right. I'm going to do 3 with you, and I'm going to let you kind of finish the notes on your own, because this stuff is easy. I'm not going to take some time, a lot of time with it, because you're tired of watching these videos by now, right? I know you are. I'm tired of making them. No, not really. I actually enjoy them. So, we have 7 plus 4j times 2 plus j. Alright? So, how do I go about solving this? Well, what's it look like? Yes, it's a complex number, but what else is it? It's also a binomial being multiplied by another binomial. So guess how we treat it? We treat it just like if we were just multiplying binomials. How do we do that? FOIL! We use the FOIL method. Okay? So first, 7 times 2 is 14. Outer, 7 times j gives me plus 7j. Inner, 4j plus 2 gives me 8j. Last, 4j plus j, 4j times j gives me 4j squared. Combine like terms. 14 plus 7, plus, that's going to be 15j plus 4j squared. Now, you are used to stopping at this point when we're working with normal variables, but j is not a normal variable. It's an imaginary number. Look at this, guys. This says j squared. J squared means what? -1. So really, this is saying 14 plus 15j minus 4. Simplify again. 10 minus 15j. Now, we have to ask ourselves, is it in this format? The real numbers first, followed by the imaginary number? Yes. So this guy happens to be 10 minus 15j. So, remember, FOIL method just like normal, but don't forget that your j squared, when you do get it, happens to be a -1. So you have to finish it out completely. You can't just stop at this part. Alright? The end. That's it. Last video of the semester. If anything that you might see throughout the rest of the semester, you might see an occasional just like, oh, I want to show you a problem that I see you're struggling on. But I may do most of that in class. But just it. That's the end of the note taking. We are done with all the material. All the material has been taught and covered. And you have a substantial amount of time left in the semester. So use these videos, go back through them, use them to your heart's content. Use those notes, use class time. This last module, this last test should be, I would actually say, is probably should be your easiest test of the semester. All right, and it's a good thing because you've got a lot more. Some of you have not even finished up to maybe your third test at this point in time in the semester, and that's okay. So you've got plenty of time to do things, and then this last module, easy peasy, lemon squeezy. The only struggle thing I would say about this module is be careful about your graphing. All right, that's probably the one thing that might struggle with. Whatever. But other than that, you should be fine. Again, you know my drill. Ask questions, blah, blah, blah. See you in class. All right, bye-bye.